Let's take a look at how the microscopic and macroscopic pictures that we've developed are connected mathematically. Our starting point for developing some mathematical expressions that connect the microscopic picture, i.e. the partition function and the Boltzmann probability, to the macroscopic picture, that is, observable macroscopic properties like the pressure, the internal energy, and the entropy, will be the Boltzmann definition of the entropy. Remember that the entropy is connected to the ensemble size and is related to the natural log of the ensemble size. Remember also that the ensemble size is related to the probability of a particular energy occurring by the following equation. If we take the natural log of both sides, we find that the natural log of the ensemble size is equal to the natural log of the partition function plus the internal energy divided by the Boltzmann constant times T. So we can plug this directly into our Boltzmann expression for the entropy to show that the entropy is related to the partition function and the internal energy. Our expression for the entropy gives us a way to develop an expression for the internal energy as a function of the partition function. Let's look back at our expression for the natural log of the partition function, and let's take the derivative of that expression with respect to temperature. When we do that, the ensemble size, if we do this at constant volume and number of moles, the ensemble size is constant, and so the derivative of that is equal to 0, and the derivative of minus E over K Boltzmann T is equal to E over K Boltzmann times temperature squared. So from there, we can solve for the internal energy and see that the internal energy is related to the derivative of the partition function with respect to temperature. The Helmholtz free energy is defined as the internal energy minus the temperature times the entropy. Since we now have expressions for the entropy and the internal energy, we can simply plug those into our expression for the Helmholtz free energy and get the following seemingly complicated expression. However, notice that the second term in the parentheses at the end of this expression is just equal and opposite to the first term, and so those cancel out, leaving us with a very simple expression for the Helmholtz free energy. Notice that the Helmholtz free energy is directly related to the natural log of the partition function. Our differential expression for the Helmholtz free energy gives us a way to calculate the pressure as a function of the partition function. Notice that the partial derivative of the Helmholtz free energy with respect to volume at constant temperature and number of moles is just equal to minus P. Therefore, if we take the partial derivative of our expression for the Helmholtz free energy in terms of the partition function with respect to volume at constant temperature and number of moles, we will have an expression in terms of the partition function for the pressure. Carrying out this differentiation gives us the following expression for the pressure. Finally, substituting the internal energy and the pressure into our expression, our definition for the enthalpy, and substituting then the enthalpy and the entropy into our definition of the Gibbs free energy, we can arrive at expressions for the enthalpy and the Gibbs free energy in terms of the partition function. These expressions are enthalpy equals kT squared times the derivative of the natural log of the partition function with respect to temperature minus kTV times the derivative of the natural log of the partition function with respect to volume. And for Gibbs free energy, it's minus kBT natural log of the partition function minus kBT times the volume times the natural log of the partition function with respect to volume. So you see that we can get all of the thermodynamic parameters in terms of the partition function. This gives the partition function a very important role in thermodynamics, and particularly in terms of making the connection between the microscopic and the macroscopic pictures.